send the score for your quiz, please check your email. Okay. Okay, last time we have discussed about the some problems for related rates. I have your TA practicing with related rates. Okay. But let me review some parts from the chain rule and also the implicit differentiation. Okay. If you have functions, maybe this start with this one. Okay. I've done this before, I think. All right. Let me start with the how to solve this with implicit differentiation. So if we have y okay, if I have y, and then I need to remove the square root. Okay, so I probably it will be easier to solve. So let's square this both. Okay, so it will be y squared x. Okay, hopefully it will be easier for the differentiation. So let's implicitly differentiate. So this will be 2y and dy dx. And this will be 1 plus, okay, 1 over 2 squared of x plus squared of x. And don't forget to multiply with the functions inside. So multiply with the 1 plus. Okay. Let me simplify. This whole thing is in the bracket actually, okay, from this one. Okay. So 1 plus, okay, let me write this as 1 plus actually from this functions, I can make a pattern like this. Okay. And you still have dy dx and 2y. Okay. And let's move this 2y to the right side. So it will be dy dx 1 plus 1 plus and then 2y is our original functions multiplied by 2 to seems we have a pattern, right? So you can also check whenever you add like x, like try 4, 5, 6, you have a pattern. Okay. This one is having 3x, right? So 1, 2, at least you have three denominator like this. Okay. I'm just showing you that with certain functions, you can have also certain patterns. Okay. Let me try with the let me try another functions. Let me just this is 3x and this is 4. Let me try like infinitely amount of x. Okay. So for example, if you have f of x, okay, it's x plus also x plus uh, as infinitum. Okay, so it will go infinitely amount of x plus x plus x plus with square root. Okay, what I want to show you here is with some simplification of the implicit, okay, I can solve this equation, and it is way more easier than the previous one. So if I make, so let my y will be this case, okay, the original function. Let me just write this and dot 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 like that. Okay, because its x is having infinity amount, I can rewrite this y equal, let's just have x, and then it's plus, actually you can say it's another y. It's the same thing, right? You have x infinity amount inside the original function also. Okay, I can rewrite this, and then like previous slides, let's square both sides. Okay. We can square root. We can square this both sides, and it will be x plus 1. It's way much more simpler. And we implicitly differentiate this. Okay? It will be 2y dy over dx. And it's just 1 plus dy over dx. Okay. And then we grouping the dy over dx. So let me write this 2y over 2x. This is 2y minus 1, okay, equal 1. Okay. And my dy over dx is become 1 over 2y minus 1. And let's see our y is our original function, right? So I can write this whole thing as 2 and then plus dot 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 and then minus 1. Yeah, just that it. So by implicit differentiation, you can do many things. Okay? Most of the proofing, like I did before, I'm proofing the, for example, the limit as h is 0. This is actually our definition for derivatives, right? We can prove other basic derivatives like the power rule, um, chain rule, the ln, the product rule like this, okay? The quotient rule, all can be proven also with the implicit differentiation. It will be like shorter version of the proof like the original proof. Okay? But remember, the definition is always, okay, the definition is always by this limit. But if sometimes you need to prove in a fastest way, sometimes the implicit, it can be an easy tool to prove. Okay, and most of the cases, if you have y in your equation, you have like this y. Okay, it's easy to use the implicit differentiation. It's easy. It's really easy. So maybe sometimes in the textbook or in the problem set, you will see some equations include the x and y, and you need to find the tangent line, equation of the tangent line. Meaning you need to find the dy dx, okay? And you need to pretty much do the same thing as this one, okay? And you draw the, or maybe just write down the equations, the linear equation from that tangent line. Okay, just a quick review. Yeah. Okay, any questions? Perhaps I'm giving you one example that you can try. I think it's similar to what we have done before, but I'm just want to check whether you get it or not. Okay. Let me try this one. I've also write these equations in the PDF that I sent last night. So the question is how many methods you can do. I can think of 3, but maybe you can have more. I'm not sure which one. Uh, yeah, let's try this one first. So try to solve this. Um, you can directly differentiate, or you may change to another form and then differentiate. So the function is the ln, and then you have the inside function. Of course, you can do the chain rule. Okay. So you have the function ln, and you have the inside functions, and the inside functions having a 2 component of functions. Right? You have x and then square root of x squared plus 1. Okay. So you can do the chain rule process. So ln 1 over something, and then you need to multiply with the product of the inside function. That you can also do. Anyway, any method you prefer, as long as it's consistent and logically correct, that's fine. Yeah, that's fine. Yeah. Hmm? Ke bawah, ke bawah sini di per. Ini kan dua ya. Iya, bagi lagi. Yeah, perhaps the easiest one is just using the chain rule, right? It's direct and straightforward. You get the answer directly. And you still need to multiply with the inside functions. And the inside function is basically the product rule. Okay? So it's FG, right? So you need to calculate the product rule. Okay, then you get the 1 over x plus 2x squared. You can simplify this. It is should be 1 and then plus x squared. Okay, we get the answer. Is 2x squared plus 1 over x and then multiply with x squared plus 1. Okay. Okay. So I mark this as our first method. Okay. This is direct approach. I will say that this is like pretty much all our calculus, okay, because you are directly doing the chain rule. Okay. So this is the chain rule. Okay. Okay. Let me write another method. So let me write the questions. Okay. Let me make this f of x. So let y is my ln. Okay. Let me making this with e. Okay. So I will have e, y, and then x. Okay. And then let me differentiate. This will be e to the y, and then don't forget dy dx. And then this will be the product rule. So same thing happened here is x squared plus 1 plus 2x x squared over. You still have the e to the y. E to the y is basically our x. So dy dx. Okay. And then this will be 2x squared plus 1 x squared plus 1. Okay, same. Okay, same answer. So you can use the e. Okay. So basically, this part we call the algebra part. Okay. And then from here below, it's the implicit. This is calculus using the implicit method. Okay. This is the second method. Okay. Let me show you the third method. Uh, okay. My method here, I will just using the law from the logarithm. Okay. So I will write this ln x plus ln. Okay. So I can write the f prime. And don't forget to multiply with 2x. Oh, let me simplify first. So it will be much more easier. I can write this okay. Okay, I think I like the last one, this method, because the way you calculate it will be not really clunky. If in a chain rule you have like a lot of functions, right? You have the outside, inside, you multiply, right? But here, with the just using the logarithm, with the log law, you can also rewrite the form and make it easier. Okay, so to solve the problem, okay, in calculus, you can have your like the algebra. So this is still the algebra. So you rewrite the form, okay, and then to differentiate, this is the calculus, just calculus. dy dx. So you can directly differentiate, or you can use some algebraic way to rewrite the form until you get the most easiest way to solve. But it depends on you, okay? Which way you prefer, it's up to you, okay? Okay, let's move on to I will have some short sections. Okay, it's the exponential growth and decay. Um, it's just really short. Okay, how to apply or how to use the exponential. Usually, we are using in the population, in the radioactive substance. Okay, because the populations, okay, every year, every 5, 10 years, it will be getting larger, right? It's increasing. While radioactive, okay, if you don't remember, radioactive, for example, any uranium or any, what is radioactive? Radium, what else? Yeah, any radioactive material, it will have radiation, right? But after some after t times, okay, this whole mass, okay. So for example, if the radioactive has mass m, the mass will be getting smaller and smaller. M is getting smaller and smaller. Okay? So in here, we do not say it's getting larger, but it's getting smaller, or we say decay. So larger, or this is growing, or in radioactive, it's decaying. Okay. Okay, how we are dealing with the rate of change with both of cases. Okay. So I will write the rate of change is proportional to the quantity. So rate of change is our derivative. Okay. In this case, because we are dealing with time, it's usually the dt. Okay. And the quantity. This is the original function. It can be mass, it can be total size of the populations. Okay. So, and a proportional. A proportional means, okay, if you have, I think in physics or in chemistry, if you have the symbols, it's the meaning is it's proportional. Okay. Or sometimes you have A is equal K B. Okay. So K is just any constant. Okay. But we still can say that A is proportional to B. Okay. Okay. And then how we are dealing with the mathematical model or the functions. Okay. So if we want to if you want to know for example, if I have yt, okay, this is my function, okay, and I want to relate these functions with the rate of change. Okay. Let's say the rate of change is dy over dt. Okay. When I say it's proportional, let's just have some k and the original function. Okay. We have this expression. Okay. By the way, this expression will be in most of the courses if you have anything that have a rate of change. In chemistry, you have rate of reaction, right? In physics, you have the radioactive. You have also the phenomenon in kinematics, fluids. You will always see this expression, proportion. Okay? And the difference is just the k. Sometimes the k will be depends on which substance, which section in science. But let's see these functions here. Okay. Uh, this function is actually it's asking. Okay, it's asking. Okay, find function uh, whose derivative is a constant multiple of itself. So from this expression, it's actually asking us if we have y, and if we derive that y. Okay, so if we have y, and we want to derive this y into dy dt, but actually in this dy dt we have another y, so the y is still inside. Okay, and it's just having any constant multiply that y. Okay. What kind of function is that? So when you derive, you will have the original function inside. What kind of function? Any idea? What? E? Yes, E. So when you have E to the x, okay, the derivative is just E to the x, right? If E to the x having 2, it's having 2, right? It's having another constant here, K. Okay, got it? So let's apply some functions to our original functions. Let our original functions be another constant A, okay, and having E and having some T. But because T is also with another constant, let's have another K here. So when you derive this, it will be K, A. So it's this both is another functions. Let's say B or maybe K, big K. Okay. What we are doing here is just to make sure that our functions is based on our approach here can be applied to some cases. Okay. Okay. And we can write this like back to the original one. It's just K and Y. Okay. This is Y. This is KY. Right. So it's just the derivative is just multiplication of a constant and the original function. Okay. Okay. Let me write some. Let me write one more time. So dy dt is ky. Okay. Let's make some definition for y. Okay. This is quantity y at time t. Okay. And then dy dt means it's rate of change. Rate of change. Rate of change of y. And it is proportional, okay, to yt at any time. And if I have the y is a, k is constant, okay, but k can be 0, can be greater than 0, can be less than 0. This is what we call the natural growth, and it's natural decay. This age is a constant. Usually, it's the initial population or initial size. Okay, the A. It can be written A, C. Okay, maybe in the engineering of math you will learn next year. I think in that course it will be C, but the same thing, same thing. Let me give you an example. Maybe just one example, and then we can move on. Okay. So to give you a perspective to see what really is. Okay. So let me give you example for population growth. Okay. Imagine this is I think in your high school you're familiar with, say, the cells, right? Microscope, right? Like you maybe from the onion or any plants you see cell of plants, right? Okay. So imagine this is uh, actual cells, okay, and this is a petri dish, okay, petri dish. So example, if this is 5,000 at the beginning, okay, at this race, it's 30 minutes, it's 20,000, but I think it's too fast when I, yeah, whatever. Usually for cells, it needs at least 1 day to be multiplied really exponential. But let's just say you have 5,000 and then 20,000, okay, after 30 minutes, okay. First is find population as function of t. Okay. First, what you need to write is assume natural growth, okay, because we don't really know what happened in the information, right? So we actually just assume that it's natural growth, that our population, maybe I will write P is our population, okay, P, dp dt is kp. So I will write the function as pt, okay. And our P is A, E, K, T, okay. When P is 5,000, let's decide P 5,000 is our initial, okay. When P is 5,000, let me write T is 0, okay. So 5,000, A, E, and it's just 0, okay. And I can conclude that from here, A is 5,000. Okay. And from the 5,000, let me write P is 5,000, E, and then K, and then T. Okay. What we need to find is K, okay, to make the models correct for every time. Okay. So let's see. The second case is 20,000. Okay. So when P is 20,000, is 5,000. E, K, and T is 30 minutes. Okay. Let's just make 30 minutes like that. Solve this, and it will be 4 E, K, and 30 minutes, or maybe just 30K. But it's not 30,000, okay? It's K constant. And solve this with ln. ln 4 is 30K. And we get K is ln 4 divided by 30. So from here, we can conclude our P as time increasing is 5,000. E ln 4 divided by 30T. Okay, this is our models. Okay. Okay, and then this is really typical questions in populations. I think, and also some of you already maybe doing this in high school also. And then the question is asking, second question, when will it be 100,000? So based on our function, let me write the function one more time. So this will be 100,000. This 5,000 E and 4, 30, and we are looking for T now. We find this, and it will be 20 is equal this E. So ln 4 30 is ln 20. So I get t is 30 ln 20 divided by ln 4. Yeah, just you can calculate if you want, but just leave as that one. And the third question that usually asking is the rate, say after 1 hour. So the rate means you need to find the derivative. Okay? So let me write pt and write dp dt is ln 4 35,000 e. Yeah. So dp dt is 1 hour is 60 minutes because before I've calculated in minutes, let's use 60. ln 4, maybe 500 over 3, ln 4 e ln 4. 60 divided by 30 is 2. 2 to ln 4. Yeah, this is the rate after 1 hour. Okay. And maybe you will be asked also for rate when reaching the 50,000 bacteria. Okay. So this basically is dp/dt is kp. Okay. So k, we already know k. So k is ln 4 divided by 30 and multiply by 50,000. And you get the rate of change reaching the 50,000 populations. Okay, that is basically all the typical questions. Okay, that can be derived from the exponential growth. Okay, same thing happened with the radioactive decay. The difference is in radioactive decay, you have reducing in number. Okay, I will get back to the sections if we have time and if you need to have more practice. But let me go to the last section in the chapter 3. Okay, and this is called the linear approximation. Okay, imagine you have the fx. Okay, you have a function. Maybe observe in a. Okay, at the x equals some value. Okay, some a. I can rewrite the df or dy dx as f prime a. Okay, at the x equal a. And I can write this in limit as x approaching a. This is fx. And this is x minus a. Basically, it's the tangent. Okay, if you see the triangle in the curve, remember? Okay. So I can rewrite this derivative. Okay, so limit definition. Limit definition of derivative. Okay. Okay. Now, if my limit here, okay, if I remove this limit, is it true or not? If I remove I erase this part, is it true or not? Is it correct or can it be equal or not? No, right? No. But here, okay, remember the concept of limit. Okay? Concept of limit is actually if having your x approaching some number, okay, so it's getting closer, closer, closer to that number, right? It's this limit definition. So if you have uh, functions, okay, let me just draw like just random curve, okay, okay. Let me observe okay, at this point. Let's say this is A, okay, or maybe A like this one. At that point, okay, based on our definition in derivative, this is, I can draw the tangent, right, in A. Not really good. Okay, better. This is my tangent, okay? Okay, now, if you see closely, we're zooming in, okay? This curve, of course, it has a curve, right? But this red color, this line, is straight line, okay? What we are doing in linear approximations, okay? In nearby this point A, we can make the curve like the line because it's really, really small. Okay? That's what we are doing in linear approximation. So I can write this, okay, this expression here. So I can write this approximate okay. It's not really equal. It's not the exactly, okay, but I can make approximate, okay, approximate. Okay. And then let's try to solve this whole thing here. Let's try to solve for the fx. Okay, so let's solve. Okay, let's solve for f of x. Okay. So I can have my f of x minus f a. I will write in equal, but it's not equal. This is just for calculation notes. Okay, so my fx is equal fa, or it's not equal. My fx is approximately fa plus. Okay. So what is actually this line? Okay. Remember when you are dealing with the equation of tangent line, it's the same expression. Okay. But what we are doing here is let me draw functions. Let me just draw functions, curve functions. Okay. Let's say this is x. Okay. Maybe x is in number. It's difficult to compute. Okay. But nearby x. Let's say we have a. Okay. And it's easy. A is easy. X is difficult. Just like that. Okay. And we can approach this ax with tangent of a. Okay. So let me draw in. Okay. So this is let's say this is x minus a. right? Let's make it bigger. So this is x minus a, and this is fx minus fa, right? Got the idea? So basically what we are doing is we are just making the tangent line equations and use that tangent line equations to approximate the fx that we want to compute. Maybe x is difficult number that we want to compute. And we can do it by calculus. Okay, we can do it. We can compute any difficult number, maybe utilizing some functions, and using calculus we can compute all. Okay. This is linear approximations. Okay. Linear approximation. Okay. Okay. The next one, what I want to show you is actually it's in your textbook. It's still in the next chapter, but I think it's related to linear approximation. But so I will give you some introductions. Okay, it's called the Newton's method. Okay. Okay. So let's say I have this function. Okay, the, f of x. Okay. This function is crossing the x, right? It's having at least this root. Okay, one root at least. Let's say, okay, let's say when fx is 0, we can find the root, right? We can find the x. Okay, let's approach from our linear approximations. Linear approximation is when fx is 0, okay, when fx is 0, so let me this 0. So I will have f prime a is negative fa over x minus a. Let's switch the f prime and x minus a. And x minus a and this is what we call the Newton's method, or some rewrite like this: x of a minus. Usually in your textbook, the x is x0 and a will be x1, but it's the same thing. Okay? Because in Newton's method, you can have like x1, x2, x3. Let me show you how. So let's say the real roots are in this part, right? So let's say you don't really know the functions, and maybe you are guessing the number. Oh, maybe around here, around here. Okay, let's just try writing this as your x0. Okay. So what really happened in Newton's method? It's crossing the curve. Okay. When x0 is crossing the curve, let's draw the tangent from this point. Okay. Okay. When you draw the tangent line across this x, okay, this become your next x. This is your actually your x1. Okay. So from your guess, the number, you're getting closer to the real answer, the real root, right? Same thing if you go here and then the x1 get the tangent also. Let me write in the different color. So you can draw from the x1 here, and you can have another tangent here. Maybe it's getting closer, right? So let's write this as x2. So this Newton's method is, until this day, still useful in some iterations, in some software iterations for computing, for computational purpose. So you can have as many as you want. Okay, so x0, x1, and this is x. Let me write this. Oh, sorry, it's not x0. It should be x1, and the a should be x0. Sorry. So this is x0. This is wait, x1. This is x0, x0, x0. And then maybe you have another x2. So x2 will be x1 minus, this is x1, and f prime x1. Maybe x3. Okay. The more correct guess number you already make, okay? Maybe you need only 2 times, and then it's okay. Or maybe 3 times, okay? Or maybe 5 or 7, but it's too much. Okay? But if you have like 1 or 2, and it's already correct to the real answer, then you can stop there. And Newton's method already proving that you can getting closer to find the real roots. Okay? And it's derived from the same idea from the linear approximations. So from linear approximations, you're getting the tangent line equations. And from here, you are looking for the x when the function is 0, when the fx is crossing the x-axis, which is this is 0. Okay, okay. Perhaps it's a little bit too complicated, but let's see what we can do if we have some examples. Okay. So let's say we have, okay, so find, let's say 9, okay, using calculus. Do you need AC calculation? Okay. What we can do here, first, let's say we are defining our functions. Our function is just, let's say, just square root of x. Right? Okay. Our x is, of course, this is what we want to find. Okay. And then we need to choose a. So we need to choose a that we think easy to be square root. This is 9.06. What a you can think that easy to square root? Close to 9.06. What number? Any idea? Okay. So what is a? 9. Okay. So a is 9 because it's easy if you are solving this 3, right? Okay. And let's see what is our derivative here. It's just 1 to x, right? And when we put a is 9. It's just 1/6, right? So let me write the whole idea. Okay. So fx, let me write the functions, all the important nodes, plus the f prime a, and then this is x minus a. Okay, and we just need to plug in the number that we want to evaluate. So this is fa is just 3 plus 1 over 6, and x minus a is 0.06. Okay, so we can compute a difficult number with the some functions, and we can approach approximately with the exact answer. Okay? Of course, if you want to know, if you want to multiply this with another 301, you have 90601, right? It has another decimals here, but um, it depends on usually, in mathematics you have error, right? Error. Okay. Error means the difference between your calculation with the real reference. Okay? That's the error. Okay? Depends on what error that maybe the software has. Right? Usually the error can be like 0.0001 or 0.00 something. Okay? Depends on that error. We can say that okay, this is actually closer to our x here. So 3.01 is still okay. 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 Okay, then to give you an idea, uh, linear approximation and also the Newton's method, let's try also some example for Newton's method. So if you have, for example, the square root of x, okay, because the Newton's method is basically the inverse of the linear approximations, what we are doing, right? What is the inverse of this square root of x? The inverse. What's the inverse? Any idea? X squared, right? Yeah, it's x squared. Do you still remember how to find the inverse? Okay, remember? Let me write it for you so that you will remember. So then that's just having y and square root of x. Inverse means your domain and range is switching. Okay, so solve for the x. Okay, so make it squared, and later you make the x as your inverse because it's switching, and the y becomes the x. Okay, so practically this x is the f inverse. Okay. So let's say we have this x squared, okay? Because our functions here is square root of x, okay? Now we have the x squared. So let's inverse our questions, okay? So if let's write another functions, x squared minus 9. Let's just write here. Okay, now if fx is 0, what is x, right? And based on our findings from this method, let's just use the number from the linear. Okay? We are using a is 9. Okay, and when a is 9, the function is 3. So let's use 3 on the inverse one. Okay, let's try using the a is 3. Okay, so based on our Newton's method, this this x will be let's write a minus, this is f a, and then over f prime a. Okay, so let's having some fa FA is when we plug in 3, is 9 minus 9.06. It's minus 0.006, right? So A3, and then F prime A is x squared, just 2x. So 2, 3, it's become 6, right? So this is 2A, okay? It's become 6. And then let's plug in our number. A is 3 minus, okay? And then 0.006, 6. So x is 3 plus 0.001, 3.01. Okay. So this is just to show you that actually our linear approximation and Newton's method is actually similar. Okay? It's actually inverse with each other. Okay? Because in your textbook, this is I actually want the Newton's method to be in chapter 3 or the linear going to chapter 4. Because chapter 4 is actually application of derivatives. Okay? And Newton's method is actually in chapter 4. Okay? Linear approximation is chapter 3. But it's the same from the same principles. Okay? So I want to give you that all the chapters you are learning, okay, in calculus, it's not really like chapter, chapter, chapter. So it's like the whole integrations thing. Okay? So you can see the linear approximation and Newton's method as uh, something that is actually the same. Okay? It's actually the same thing. Okay, okay. Let me go some examples. Okay, some example. Okay, uh, compute square root of 17 using calculus. And the second one, compute the okay. Try this two questions. So you need to try the questions without using any calculator. Okay? So square root of 17. To begin with, look for the close number that when you square root, you can get the number easily. You can get the results. Okay. And also, this is also same, okay, 1.998. But the difference is make sure the signs, okay, positive, negative. Okay. This is less than 2, right? But that is more than 1, more than 16. If you want to make 16. So this is more, this is less. So of course there will be like one will be plus, one will be minus. Okay, I think number one, we can just use the original square root of x. Okay, I will write directly. F 17 is choosing a 16. So this will be square root of 16 plus the 1 over 2 square root of 16. And because the difference is on 17 minus 16, let me write this. Okay, so it will be 4 plus 1 over 8. Or it's just 1. Okay. Okay, the next one, the 1.998. Okay. Let me write this as the x to the fourth. Okay. The functions. Okay. And of course, because it's obvious, right? It's 1.998. If you want to see, it's just 2, right? So let's just make 2 as our a. So f this should be approximate. So this will be 2, 4 plus, okay. Uh, and then 4 to 16. This is minus 0.0002. And then multiply by 32. So it should be so it will be 15,936, right? Yeah. Okay. So sometimes, okay, sometimes you making some mistakes here, x and a. So you are mixing or switching the x and a, and then you are ended up with plus here. But remember, this one should be less than 16. So the answer should be less than 16. It can be, it cannot be more than 16. Okay, that's the logical sense. So if you want to check your answer, look at the original function and what the number will be look like. Okay, so from there it should be less than 16. So it's true here. Okay. Okay. Um, Any questions? Okay, then I can move forward. Okay, I can move forward. Okay. Later, if we need some time to go back to linear approximation, we can go back. But the Newton's method, I will maybe review again after we uh, after we go to chapter 4. I will review again. But at least for linear approximations, at least you can solve some problem. Okay, now I'm right in your notes in the PDF file. Okay, if you have let's say this positions t cubed 60 squared plus 90. Okay, the question is, what is the average velocity and what is the average speed? From these questions, I will link to the next chapter. What's the important from this applications? So it's physics, okay? It's physics, okay? Having the velocity, speed. Of course, if you see any st, it's position or distance. So it's asking average velocity, average speed. When t is from 0 to 5. So first is you need to know what is the difference, okay, between the velocity and speed. Okay, velocity is just the um, change in position divided by time, and speed is distance total distance traveled divided by total time. Okay. Okay, this is in t in seconds. Okay, and s in meter. For average velocity, I think it's just change in position and change in time. So you can write this average velocity as s5 minus s0 divided by just 5. Okay. Let's check our s5. Okay. What is happening? 1, 2, 5. 25, 6, 45, 25, 20, right? 20 meter. And S0 is just 0. So our average velocity is 20 divided by 5. It's 4 meters per second. Okay. Based on this definition, it's already correct. Okay. So let's go for speed. Average speed. Let me write average speed is total distance travel divided by total time. Let me write the functions one more time. T cubed 60 squared plus 90. Okay. So total distance traveled. We already know this is 20. S0 is 0. Okay. So how to make sure that you knew that what is happening here? So you have functions, you have total distance traveled. How will you know the how long the distance is traveled by this case? Just look at the equations. Okay? It's cube, right? What's interesting in cube? If it's quadratic, maybe I can say that okay, the guy just moving forward. But when it's cube, maybe the guy will be he's moving and then he's back and move forward, right? But how can we know that? How do we know that? Yeah. How do we know? Yes, yes, of course. So that's the first case. Okay. So remember that when we have, let me draw just any curve. Okay. Maybe that not that, maybe, yeah, like that. Maybe just this. Okay. Easy to see. Okay. If we let me if this is the graph, okay, this is just illustration, okay. When it is starting uh, at the origin, okay, it goes up and see the gradient. Okay, see the gradient. So gradient here is still here, still here. The gradient is getting horizontal, right? So its gradient is positive, 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 and then at the horizontal one, it's 0, right? Okay. We can say also here is, let me say this is the f prime, this is gradient, is positive, okay? Yeah, positive. So positive, 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 right? At specific point here, at the horizontal one, the gradient is 0. Okay? When the gradient is 0, what just happened from this curve? It's positive and then negative, right? So we can say also this is we call some called it is the turning point. Some also called the stationary. Some is calling critical. I think our textbook is calling critical point. Okay. So let's check. Okay. Let's check our gradient. When it's 0, what has happened? Okay. So from here, let's check our ds over dt. Okay. Which is the gradient of the total distance equations. Okay. So it's become 3 squared 12t plus 9, right? And we need to look for this point, okay? In case that the person is going forward backwards. Okay? So let's solve this. This is 0. So 3 squared 40 plus 3, right? Yeah. So t is -1, -3, right? So we got from here t is 1 and t is 3. Okay. Let's check S1. 1 is -5 plus 9 is 4. And let's check the 3. 3 becomes 3. 27, 27, 54, 54 is 0. Yeah, it's 0. So the position is back to the first one, right? So let me draw some picture. So this is the person is running. It's running. Okay. This is the t equals 0. Okay. And then when t equal 1, it's 4. Let me maybe here. So it's going 4. Okay. Or maybe 4 is maybe here. So this is 0, 4. The red is for position. The black one is for time. So t equal 1. Okay. And when t equal 3 is back to original position. So 4 and 4, right? So 2 times 2 times 4, right? And then after that is rushing to so let me write this. T equal 3 is also 0, and t equal maybe 5 here. And from 0 he go rushing to 5 to 20. So the total will be 20 plus 4 plus 4, right? So it's 28. So average speed become 28 divided by 5, which is the 5.6 meters per second. Okay. Get it? Okay. That's in physics you already learned, right? Yeah. So this is just maybe reminded for physics, and also a guidance for the our gradient. Okay. This is we call also at this point. Okay. At this point, this we call this is the extreme value. Extreme value depends on the functions. In this case, this is maximum. Okay. This is maximum. And if it is just observing, if this function is just like this, then we call this is absolute maximum, this point. Yeah. But if the actual function is really big and this is only part of the whole function, we call this a local maximum. So, for example, if you have this function, okay, you have whole functions like this. Okay, this one is local max, okay, and this is local min. Okay, where is the absolute max and min? This and this, right? That's absolute. So in this point, this is absolute max. This is absolute min. Okay. If for example, this having open interval like this means undefined. Okay. Meaning there is no absolute min here. Okay. Okay. And this will um, give us idea for extreme value. And we will start the chapter 4 with the mean value theorem, and then we go to extreme value and go to how to sketch the graph and the second derivative. Okay. So hopefully it will be on the next Thursday. So I will just stop here. Okay. So maybe any questions first? Any questions? Questions? How about your quiz? Is it okay? You happy? No. Okay, it's just the first quiz. Okay, don't worry. Um, I'm planning to have at least three quiz, at least three, at most maybe four, three or four. Okay. Uh, the next quiz may be about the chapter two, chapter three, four, or maybe only chapter three, meaning the all the derivative, the inverse of trigonometric, the related rates, and so on and so forth, up until the linear, up until the linear. That will be the second quiz. Or I can combine with the next chapter, but later we will have quiz. We will see if we have time. We can arrange our time. And the midterm, the midterm is around November, maybe the first, maybe the second week of November. Uh, Hopefully, I can finish the chapter 4. So chapter 4 finish. Then the midterm will be 1 to 4. 1 to 4. Okay, I think that's just for your information. Okay. Uh, can you check this is true or? Oh, okay, okay, okay. I haven't checked this one. Okay. Let me let me write in the let me write here first. Okay, I will check. And what's the other? This one? Yeah, this maybe some mistake here. Some mistake in calculation. Should be 2/3. 2/3. Two over three. This one. Right? Yeah, 2/3. I can give you this the full is 15. So I can plus 13. Okay. So let me write your ID. So this is okay. Mhm. Okay. 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 Yeah. Yeah. Same. Same. Let me plus your anything else. Okay. I can make plus. Okay. Plus 15. Okay. Wait. Should be how will you get the x here? Can you oh wait. It's plus 10. Yeah, but 4 is correct. 4 is correct. Minus 4 is correct. Yeah, but it should be, there is no x here, right? Oh, yeah. Okay. I didn't realize that. Okay. Okay. I thought this is x. Okay. Yeah. Maybe next time if you want to make, yeah, just dot. Yeah. Easy for me. Okay. This is correct. This is correct. Yeah, because your writing is not clear. Okay. Yeah. Yeah. Yeah, this is correct. This one. But because you didn't write the theorem, but I can add more. This is now. I think this is should be 15, but I can give you 12. Okay. So, okay. Which one? Here. Okay. I can give you a few points. Okay. Because I'm following you and then oh why it's circle like a circle. Okay. N plus 3. Okay. 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 Ya, yang selanjutnya lebih bagus. Kan kuis cuma berapa persen? Ini kan kuis. Kuis. Ya ditotalin 15-20. Kan? Oh,